And the answer, I guess, if you look at the schedule, is I'd scheduled in an exam review for Monday morning's class. I wasn't sure I'd have it graded by today, but of course, then we went to doing it on WebAssign, and it automatically grades itself. So that's why I didn't schedule the exam review today. Today we're doing Compton scattering. We'll talk about that here. So here's what I had no idea when I put the schedule together. I had no idea who was in the class. I had no idea how many people, anything like that. But Monday's class is optional, I guess. If a number of you got perfect scores, so apparently you knew how to do the problems. So for me, watching me going through the problems again probably isn't any value. But Monday morning, 11 o'clock, we'll come in. Whoever wants to come in, go over some of the problems, we'll do that. Fair enough?
11:30, right? Or 11?
Yeah, normal time, 11. What did I say?
You said 11, but that's
okay.
fine.
11:30. Yeah, normal class time. Optional class. I'll be going over the exam solutions for the problems that you want to see done. So I just your curiosity has to stay through the weekend, and I'll go through each and every one of them with you. How long did it take you roughly to do the exam? Most people, I predicted somewhere between an hour and an hour and a half. Was I in the ballpark?
Yeah, thanks.
Pretty close.
Yeah, probably an hour and a half, but
Hour and a half.
of course I did like 20 minutes here and a little bit
Yeah.
more over here, and
Yeah.
you know.
Okay, that's about what I was shooting for. Okay, great. And everybody did really well. Hour and a half. Okay, not so 90. Yeah, there's an adage that says the time for a task always expands to fill the time that's available. And so, if you were sitting in a classroom and you had to move somewhere, you might have gotten it done quicker. You had to hurry a little bit. So hour and a half's about right. I don't have any guilt on that. So that's probably the right number. Okay. Today we're talking about Compton scattering. I do have a bunch of polling questions to start off with today. Anybody have any questions before I get started about Compton scattering? Yeah, it's an interesting phenomena. And I think somebody asked me when we were talking about, say, photoelectric effect, or when we were talking about, I guess, black body radiation, not so much, X-ray production. Why were we not using, we went through all the trouble to develop energy equations that were relativistic in nature, okay? Why were we using classical kinetic energy for those phenomena? And the answer, of course, was because we could. The particles were always moving slow enough. The electrons in the cathode ray were moving slow enough that we didn't have to use relativistic effects. But in this Compton scattering experiment that Arthur Compton did in the 1920s, these high energy, I guess, gamma rays or X-rays, high energy rays, electromagnetic radiation just outside the visible spectrum, well above the visible spectrum in frequency and therefore energy, are coming in and they're making that electron move at relativistic speeds. Okay, when the X-ray or whatever it is hits an electron, it moves fast, and so you can't use classical kinetic energy anymore. You have to use those equations for energy that we developed, and I went through that in the video last night. Not going to repeat it. If you want to see where this equation comes from, we did what you did in Dr. Tech's class, or whoever taught you a basic physics 1. We conserved energy and we conserved momentum. 2 equations, slap them together, and you get a result. And so I always hate this diagram a little bit because it's really 2 pictures in one, and we should avoid that. The before picture and the after picture shouldn't really be drawn in the same place. And I just want to make sure it's clear what's going on. Here's the before picture. You got this X-ray.
I can't
Wait,
see
are
anything.
you sharing screen?
I will in a second here. Yep, thank you. No, I meant to be, but I'm not. Thank you for stopping me. So let's share the screen. Yeah, okay, now you should be seeing it. Okay, so we always get this one picture that's all in one. It's really 2 pictures here. Here's the before. There's that blue X-ray right there coming in. And before, you have an electron, which is just sitting there at rest. And so the energy is HF. I prefer HC over lambda. You'll find most physicists seem to like to talk in wavelength. If you take Dr. Kaiser's optics class, you'll spend a lot of time talking about wavelengths as opposed to frequencies. You can go back and forth, but we tend to default to wavelengths. So that's how we think of energy. Of course, the electron has no kinetic energy. It's just sitting there, but it has its rest mass energy. So that's the before picture. And then the after picture, like any other collision that you did with Dr. Tech or whoever taught you basic physics, the after picture, a different X-ray goes off in this direction with a different frequency or wavelength, right? And the electron goes careening off that way at very high speeds. So that's the after picture. And now you can see the electron has both kinetic energy and rest mass energy. And photon has a different energy as well. We're going to call the X-ray a photon, use those words synonymously. So that's the before and after picture. And you can see that angle theta right here in this equation. Well, that survives in the derivation of the Compton scattering shift. And so what Compton's talking about, and I either say final, initial, IF subscript. The other subscript you'll see is no subscript on the initial, right? So that's the initial, and you put a little subscript on there for the final. And so what we're talking about is how big is the shift, okay? And it's, oddly enough, equal to a nice constant, okay, that you can calculate, called the Compton wavelength. You can see it's a pretty small number right here, okay? Thousands of nanometers is this shift. So Compton had to have a pretty sophisticated apparatus, and I talk about that. He actually couldn't make a diffraction grating. He had to use the atomic lattice separation in a calcite crystal in order to create a diffraction grating out of planes of calcite. And that served as his diffraction grating. And so he was able to detect these small shifts in wavelength when an X-ray hits an electron and it scatters off. And the only other question, I guess, is, well, where's the electron coming from? You know, he could have done this with metals. I think his experiment, he chose carbon, which apparently has, and I'm not enough of a chemist to know why, has a bunch of electrons which are fairly free, okay? And so if they're not bound tightly to any atom, these electrons that the wavelength hits, then right there you use the mass of an electron. Okay. On the other hand, if it's a tightly bound electron, you might have to use the mass of a electron and maybe the nucleus that it's bound to. And so then the shift would be even less because that mass in the denominator becomes pretty small. Okay, so Compton's effect, Compton's scattering, and this is called, and it's different from classical scattering, which was known in Compton's day. So now it becomes, what are we up to now, the fourth or fifth experiment. Let's see, we talked about spectra where things were discrete colors corresponding to discrete energies. And then we talked about black body radiation where Planck comes up with this constant times frequency as a packet of energy, okay? And photoelectric effect, absolutely. Einstein explained photoelectric effect with a packet of energy, Planck's constant times the frequency. We talked about X-ray production, the Bremsstrahlung process. When the electron coming in slows down, it emits a packet of energy called a photon, and the energy that's emitted is the change in the energy that the electron has as it slows down, and it's exactly equal to the Planck's constant times the frequency. And I was trying to count as I was talking there. I guess this would be the fifth then example of where energy seems to be in electromagnetic radiation in these packets, which we've come now to accept the word, called a photon, and the exact energy is Planck's constant times that frequency. So for a particular frequency, there are only particular energies that can exist, and multiples of those energies, obviously, since H is a constant. And so that's the significance of it. And now let's go on to a couple polling questions. And so let me open the poll and get the right one, which is always fun to do because it's launch the poll and go to the next guy. And yeah, my pretty slides aren't all that good, but which of the following, let me I'm not blocking what you're seeing. I'm gonna make this smaller. And so hopefully I can put this right over here. Yeah, I don't know where to put it. I arrange my screens and it's always a question. All right, looks like 5 people are in, thinking it over. And I suppose the real point of this question is not what the answer is, but why it's the answer. Okay, why it's the answer. All right, everybody's in. Everybody got it right. Share the results. Perfect. You guys are great. And the only reason I guess is, this is sort of in the order of the electromagnetic spectrum, increasing frequency. So F here is going up, which means wavelength as you go that way is going down, right? Visible light, we said the wavelengths were somewhere between, I think we said 400 to 700 roughly nanometers. Okay, and if you look at the last slide, you can see that the absolute biggest the shift could be right here is Compton's wavelength, which is in the thousands of wavelengths. So you're just not going to see it, right? Is the point. You're just not going to see it in anything that has a pretty big wavelength, which these guys would. But as the wavelength gets smaller, like maybe an ultraviolet, but definitely in X-rays, and then the next thing up is gamma rays, you'll definitely see the shift in that case, okay, because the magnitude of the thing. So that's the reason E is right. So good work. Let me move on to the next one. Stop sharing. You can read it while I'm shifting screens here and launch it. So which angle gives you the biggest scattering, the biggest shift in wavelength, I guess? And we're split between two numbers. If you don't have the equation memorized, I'll give you that. I'll erase some of my junk here. That may help. All right, one more person. Give you a second here. All right, everybody's in. I'll end the poll, share the results. All right. And so let's remind ourselves what the equation is. It's a shift in wavelength, right? What it is at the start minus what it is at the end. It's the Compton wavelength, which was those constants. By the way, I mentioned this. I prefer this way to find the Compton wavelength. Okay, and I'll say why in a second. Let me finish the equation. 1 minus the cosine of theta. And the way I had it written on my screen is I had that canceled, but you don't want to do that because remember, we said that's 1240 EV nanometers, right? That's a number you might soon have in your back pocket because you learned it. And then MC squared is 0.5, and that's EV nanometers. I got it backwards, 1240 EV nanometers. And then this is 511 mega electron volts when you multiply by C squared, right? Rest mass energy of an electron is 0.511. And so I find it easier to do the math when you get that. It's roughly 0.002, okay, nanometers, which is all I can remember. But now the real question is, how's the biggest I can make this? And I think those of you that picked the 180, you recognize that becomes -1. And so this would double whatever the Compton wavelength is. That's the biggest possible shift that this experiment could realize, twice the Compton wavelength. So if I'm right, and I think I am, let me go back to the screen that has that constant, 0.0024, okay? We'll carry one more digit here. If that's as big as the Compton wavelength could be, 0.0024, then the biggest shift you can possibly see is 0.0048 nanometers. Again, going with the previous question of why do you not see it with visible light? If I have a laser of 633 nanometers wavelength, because it's a helium neon and it's in the red, if you had the Compton shift occurring, and you do, okay, because you put the laser on an electron and we're able to make it recoil away, you'd see 633.0048 nanometers as a result of that interaction. And that difference that you'll see is just, it's not going to change the color of the light at all. It's way to what the economists say, to the right of the decimal point, right? It's not noticeable. Your textbook talks about a shift in wavelength over the wavelength as a percentage. It's just a very small percentage. So you just practically don't see it for the visible light and below. All right, so 180, that's just a little kind of a math question, right? To get cosine of -1. If you don't know cosine of principal angles and sine of principal angles like 0, 90, 180, 270, 360 degrees, think about just drawing a little curve for yourself, right? What's a cosine curve look like? And that's the point we were looking at right down at the valley there when it's -1. Not sure why I didn't see it, but good job to the 3 people that got it right. All right, here's the next one. And we'll stop sharing here. Let's see, now I can go on to the new one. Yeah, launch the poll. Remember, what we're talking is the shift here, okay? Not what the wavelength is, but how much the wavelength changes after the X-ray hits an electron and then scatters away. One more person, one more, I don't know who you are. All right, I'm going to end the poll. I always hate when this happens. I'll share the results with you. And I guess if this is the equation for Compton scattering right here, and of course, this is what I just said, it's HC over MC squared, a constant. What I notice about the shift here, well, it's a constant and an angle, isn't it? And so I guess I'm a little confused why B. Okay, it seems like the shift is the same. Anybody at the same angle, this is really, the shift is only a function of the angle of that the photon is scattered. Okay, if you go back to my picture, it's only a function of that angle right there. Okay, that's, look at the equation, the shift. Now, what the particular wavelength would be, well, you put in higher, a larger wavelength, you'll shift by the same amount. You put in a lower wavelength, you'll shift by the same amount. But the shift is going to be the same for all incident energy photons. Is that confusing to somebody or anybody? I'm actually surprised that 4 people went for higher energy for greater for an incident photon has higher energy. Is that okay if I convinced you, or are you still back on what you were thinking? Well, nobody's complaining in chats. Nobody's, so I'm going to keep moving. But yeah, it's the shift, only a function of theta. I will say one thing about 180, and if you think about it as an experimentalist, because that's what I am, a theoretician would say, of course, 180, right? But let's think about what that means. Okay, so that would mean you're bringing in something like at a grazing angle right there, and it, there's your angle of, there's your 180 degrees. Well, 180 degrees exactly kind of means you don't even hit it at all, right? Or maybe you just kind of that would be a really hard thing to do experimentally. Okay, so that's the one thing about the 180-degree angle we were talking about in the last problem. But that's all we're saying. Any electromagnetic radiation that comes in and scatters like this has the same wavelength shift, according to Compton's math. All right, we'll stop sharing this. Maybe I did better here on this one. Whoops, I didn't do that. It did it on its own. Go back to that one. You'll see that question in a second here. This is sometimes helpful to think about. And think about conservation of energy. That's kind of how I view this. Think about the before picture and the after picture. One more person. All right, everybody's in. And I think the majority are here. For the other three folks who went the other direction, I would just, conservation of energy is as good a way to think about this question as anything. So what do you have at the start? You got the energy of the photon. I'll use that for photon coming in. Okay. And then for the electron, all you got is mc squared, right? And then when the collision is done, you have the energy of the photon coming out. The electron still has rest mass energy, but the electron also has its kinetic energy. Okay, and so I don't know. I used a relationship that I didn't use this one. The gamma minus 1 times mc squared. Not erase that. Gamma minus 1 mc squared. I actually combine these two into one where the energy afterwards. But the point, I guess, is this must be lower, right? The photon coming out, the scattered photon here, has to be lower than what you started with. Less energy. I've lost some energy because it went into the electron right there, into kinetic energy of the electron. Okay, so if the energy is lower, that must mean that the denominator here is bigger, right? The wavelength got longer. And so that's why B is the right answer. And the 5 of you to pick that, you went through that. You could probably look at Compton's scattering equation directly, but I think it's always good to step back and think about energy in a problem, especially one like this where we are conserving both energy and momentum. All right, last one, and then we'll start doing, we've got 2 problems to do on worksheets. We'll split up into breakout groups. Let me stop sharing this, do the last one here, launch the poll. And watch your units, and this is 10 to the minus 10th. Remember that a nanometer is 10 to the minus 9th. So think about where the Compton wavelength shows up. kind of a 50-50 choice here, right? Either add it or you subtract it. It's really a repeat of the last question, if you think about it. Just a numerical repeat of the previous question. All right, 2 more folks. 6, 1 more. All right, I'm cutting it off. Somebody must have internet trouble here. All right, and the answer is exactly right. Same as before, the wavelength has to get longer. By the way, just as an aside, this 10 to the minus 10th meters thing, it's a little archaic, but opticians used to talk about an angstrom. That was the unit. And 1 angstrom was 10 to the minus 10th meters. Okay, and if you wonder why an angstrom, if you look at an atom, like the simplest one, like a hydrogen atom, the size of an atom is just about 10 to the minus 10th meters. Some are a little bigger, but that's where the angstrom came from. Okay, it was roughly the diameter of an atom, as known by the scientists at the turn of the century. Just as a kind of a data point on that, just to kind of the scales that you have to be aware of, the nucleus right here that I've drawn as a dot is actually around 10 to the minus 15th nanometer or 15th meters. So factor a 10 to the 5th less for a nucleus. And so my scale is obviously way wrong. I've drawn it maybe a 10th the size. It's 1 over 10 to the 5th the size. And so one of the things we'll be talking about, not next week, I don't think, but the week after, is how much empty space there actually is in an atom. And that's a remarkable result from Rutherford, but I digress. Angstrom, that's where people talked about 10 to the minus 10th as a unit. All right, I'll stop sharing that and put this away and stop sharing this. How's everybody doing? Yeah, okay. Yeah, all right. Where'd the 3 come from, though? Because I think if you do the math, whatever. I think it is. I mean, the biggest it could be with 90 degrees, right? 1 minus cosine of 90, so it's just 1. So the shift is the Compton wavelength, right? Now, let me go back to sharing this. Share. Nope, I'm not sharing that. So let's stop sharing that. What am I sharing with you? Who knows? I've been sharing my email or something. Share. So we agree this, right? The shift in wavelength is equal to the Compton wavelength times 1 minus cosine of 90 degrees. That's 0. So it's the Compton wavelength is the exact shift. All right. Yeah. Now another angle, it could have been a different value, but the problem specifically says a 90-degree scattering angle. All right. Stopping to share here. And I want to just show you the 2 problems. We'll break up here. I'm going to take about 15 minutes to do them. To share my PDF. There's PDF. PDF, there it is. Acrobat, share that. And the first problem is, well, as you can see the geometry there. I give you some initial numbers. You work through what the wavelength is using the Compton equation. But then I'm asking the question, go back and think about conservation of energy, like I mentioned in one of the polling questions. Hey, what's the kinetic energy of that scattered electron? Okay. So that's what one of the groups will do. We'll break up into 2 groups of 4 here. And then the second group, I think your problem's a little bit harder. It's a little bit longer, I think, but the same idea. This time you've got an initial energy photon, from which you get wavelength, right? Draw the sketch, write an equation for conservation of energy, conservation of momentum, and then solve for the recoil velocity of the electron. I actually see 2 ways to do this problem. You can do it the way I've set it up here, where you write conservation of energy, write conservation of momentum. You can also take a similar approach to problem 1, where you figure out what the new wavelength is and figure out what the change in energy is, get the kinetic energy, and then work back that way to figure out what the velocity is. Again, using relativistic energy as opposed to classical energy. Okay, so we'll break up here, talk about the 2 problems, and we'll see what the computer decides to do in order to who gets which problem. 2 rooms automatically. Okay, group 1, doing problem 1, Amaya, Justin, Max, and Prince. You guys have group 1. Somebody in there. Okay, Max, you usually use your whiteboard, I guess. And then group 2 is Inaya, Sam, Saeed, and Shniha. Okay, opening the rooms. See you in about 15 minutes. I'll stop by.
Hey, I can't share my screen.
Huh. All right. Let me. I've done nothing different this time. Let me leave the room. I'll go back to security and be back in just a second.
Okay.
Still nothing?
No, nothing.
Technology, gotta love it.
Always.
Somebody else want to try? Because the other group is their screen's sharing. So right now, I would tell you to use this thing, as terrible as it is. Okay, do you see the whiteboard?
Yeah.
The problem with it is we found in my other section that when we clear the breakout rooms, that goes away. And so you got to do a screenshot of it, maybe.
I mean, with these kind of problems, I don't think it would be that bad to just talk through it.
Okay. All right.
If
But you
that,
do
that
need,
might
I
be the
mean,
easiest.
at the end of the day, though, you need a numeric answer.
Yeah.
Can't say it, try it?
No, I've
Do
tried
you
it.
not have your iPad?
I can't. No, it's the same, unfortunately.
All right, I'm going to close that up. The other option you can always do, if you open up a Word document, this is me playing in my with my morning class to show them, and then you get these little pens. Now, this was writing with my mouse here. This is writing with my trackpad, which took a whole lot longer. Mouse, I find, works better, but that's another option. That's what Max Tucker does, right?
No,
But I still can't share my screen if I do that.
Somebody else try to share a screen.
the thing is, it's not about notability. It's just it says the attendee screen share is just disabled. Nothing. You can't
But
share
it's
anything.
not. Hang on, let me see if there's because I did the security and I went to security and I authorized it. But more importantly, the other group is sharing a screen right now.
Weird. Must be a bug.
So let's see why it's not letting you. I'll tell you what we could do. Let me stop sharing.
You know, I guess you're just gonna have to do the problem for us.
Yeah, that's what happens, I guess.
I have a suggestion. So next to the screen share, the green button, there should be
Yeah.
an arrow for you. And that's another place where you can do it.
Yeah.
Or you can make one of us co-hosts.
Yeah, and that I'm okay with that. I just hit multiple participants can share simultaneously. Who can share?
I got it.
Hey. Oh, you
working
got
now?
it. Okay, go ahead.
Yep.
Yeah, it's
All
good.
right. That's bizarre. I've never had to do that before, but I
That
hit
is
that
weird.
button and it freed it up for you.
Interesting. I think it makes sense because the other room maybe is still sharing, and that's what it
But we've
makes.
done it. We've done multiple before. Anyway, go ahead with the problem.
Yeah. Sam, you want to go ahead?
Yeah, I can. There we go. I thought it was on my end.
Well, it's Zoom's end. There you go. All right.
All right, thanks.
Whoa.
You bet.
All right,
Okay,
so
so
we
for the drawing,
looking at something like this.
yeah,
where-
so it's almost like it barely touches. Yeah,
Yeah,
Yeah.
I tried to draw that with, but
That's
this
pretty
is as
good.
good as I can do.
it's
Where
pretty
we
good.
have it kind of going that way.
And then for the equation of conservation of energy, do we just take the generic one that we used in physics
Yeah.
1? And it's
No,
just
because
like
this
you
is
apply it.
relativistic. You got to use relative. You got to use special relativity.
So should
The
there
one
be
where,
should
yeah,
it be
the squared
HF equals HC over wavelength equals gamma minus 1 MC squared? Is he still here?
I'm still there. Yeah.
No, the one
Did that sound
equating
right?
energy and momentum of, I think that's the one we need to use.
Yeah. Multiple ways to work this too. Yeah. Go ahead and write something, and we'll
So
I mean,
I'm
if I
thinking
remember right, we had something like this.
that is momentum. That would be useful in part C there.
And for then the rest energy. That's really
Okay. And so I guess the question is, what is the energy of the photon at the start? And what's the energy of the electron at the start?
the electron.
That's the energy of the electron at the start, right there.
That should
MC
be
squared.
the 5.
Yeah, you could go symbolic. Eventually, you're going to put that number in. I don't disagree.
And
the photons is given, I think.
Well,
Yes.
symbolically, though, it is just HC over lambda, right?
yeah. Should okay.
And that's equal to gamma minus 1 MC squared. But do we need that part?
Plus rest mass energy as well.
Yeah, so just gamma.
And the answer is
MC
yes. You need
squared.
the photon afterwards, and you need the kinetic energy and the rest mass energy of the electron afterwards. So go ahead and give me an equation here. Where is it writing on it? Yeah, that's energy. So under B there.
Need a before and after. So before we have and the electron was
MC squared, right?
MC squared.
Okay, then afterwards, same HC, but over a different wavelength, right?
Over the
Call it prime or final, whatever you want to call
yeah.
it. HC over a different wavelength. And then you got two choices on what you want to write here. Total energy of the electron is gamma mc squared, right? Or you can write gamma minus 1 mc squared, which is kinetic energy, plus mc squared, which is still gamma mc squared, right? So it's kind of up to you.
On my paper, I did gamma minus 1.
Okay, but then don't forget the rest mass energy. So that minus 1 that you're subtracting off, now you got to add it right back on. So why not cancel it right there? Right?
Oh, okay. Yeah, that makes
See
sense.
that minus 1 right here cancels that. All right. Now, we're good here. That's the first equation. This is the momentum of the electron. One of the things that we've determined is that the momentum of a photon is just h over lambda. And if you didn't think about why that is, remember that energy squared is equal to mc squared plus momentum squared c squared. Go back into chapter 2 if you've forgotten that. For a photon, it doesn't have any mass. And so that means energy is equal to PC, right? And so momentum is equal to energy divided by the speed of light. And then look at this equation right here, and that just means it's what I said. Momentum is h over the wavelength. And so when you're writing out C, that's what you want to do. Start with the momentum of the photon before, the momentum of the electron before. What's the momentum of the electron at rest?
0.
0. Okay. And then that's equal to momentum of the photon afterwards.
And then just thinking ahead, we would make these two equations equal to each other for recoil velocity.
Well, write it out and you'll see what, hopefully you'll see what you got to do. Now, I'm wondering, did I lead you astray on something? Because I drew a picture I declared to be 180 degrees, and now I'm wondering if that picture may have been wrong. Because this says head on, and so this is like two balls hitting, and the ball bounces right back.
We're really.
So is that 180 degrees, and was what
Are
I
we
draw?
thinking of something like this?
And then it
And
bounces
then right back.
right back.
Yeah.
Yeah, so I might call this one a 90 degree then. And so I'm going to have to recant with the other group because I think this might be 90 degrees right here, whereas 180 hits it and comes right back. So that's the problem I was thinking of when I wrote those words.
Would that change our equation?
Yeah, it will, because right here you're going to have h over lambda, and then you're going to have the other photon, but it's going in the opposite direction, and momentum's a vector, so you give it a negative sign. Okay, plus 0, and then you'll have for the electron, where this is the speed of the electron. See the momentum equation?
MV, yeah.
And now remember, where's the answer? The answer to the problem is unfortunately in two places. It's sitting right in there in gamma, and it's sitting right there
yeah.
directly. And so the deal here is you got to work a little algebra to combine these two in order to just get either gamma or u, one or the other, and solve for what the speed is.
And this wavelength right here is our
Final. Yeah, it's the same one as up
final.
here.
Yeah.
Yeah, those two are the same.
So it's hitting the electron at rest. It bounces
Right.
back, and the electron starts kind of drifting in the positive x direction.
Yeah, exactly. It goes in the positive x direction. So here's my hint. Just a little algebra. Multiply every term here in the momentum equation by c. And then look what happens if you add the two equations. That and that actually cancel, don't they? And that's my first hint on algebra. When you give there's multiple ways of two simultaneous equations being combined. That would have been my recommendation. And then out of these two equations, write one equation. Looks like it'll be 2hc over the initial wavelength, right? And you know that. I think somebody said the initial, this guy right here is given is 0.3 mega electron volts, right?
Yeah.
So you know that
Add
number.
that over.
And that should get you started. And the hard part will be the other side. I've left you guys the hard stuff, which is this and this combined together. All right, I'm going to go to the other room, see how they're doing.
Okay.
Okay.
You strap.
I kept on getting it wrong, but then I came back to it.
Yeah.
I agree with this number right here. Let's see. So I agree with your 31 picometers. That looks good. The energy. What'd you guys do on the energy? Okay, plus mc squared is equal to, yes. Here's what, but this would be total energy though that you found. Okay. You need to subtract, but total energy isn't kinetic energy. Let me add something here. Annotate. So it asks you for kinetic energy, so it would be kinetic energy, right? Plus the rest mass energy, mc squared. That's total energy. So you are solving total energy here, but that's not what the problem asks for. It asks for kinetic energy. So I think that it actually, you made it a little harder because doesn't that term cancel that term?
Yeah.
Right? Yeah, so you added, you've got you've answered the question, and this, I think this number is even right. It's just not answering what you were told to do. Yeah. And so do we have the rest mass energy in joules? Maybe in the front cover of the book. I've got it memorized as 0.511 MeV. And I think, do they have it in joules? Yeah, no, it's not. You have to work it out. All right, let's see if I agree with that number. That one looks better. Still off though. Yeah, 10, 2 point, yeah, so yeah, 10 to the minus 16th joules. Yes, I agree with that. How'd you get MC squared so fast? Did you literally go mass and then multiply by the speed of light squared?
Yep, I have it saved in my calculator.
Gotcha, in joules. Okay, so if you got it saved in your calculator, and it made it a pretty easy calculation. Okay, looks good then. Let me close the groups here. We'll see if the other group's done. They had the harder problem, admittedly. So we're going to stop the breakout rooms, close all the rooms, and return to the main session.
Yeah, we're not doing too hot on ours.
All right, well, we'll go over it. You got the harder problem. I'll show you what I did.
Once we kind of switched up our situation, I kind of lost you.
Okay, well, let me show you. There's photoelectric. I'm finding my solution here, and I'll pull it up. Hey, group one though, would you pull up yours and show what you did? And I think you've got permission. We only got a couple minutes here, so. All right, who's talking?
Well, we solved for the wavelength, the scattering wavelength, and then added that to 30 for 31.212 picometers.
Yeah.
And then we did conservation of energy is HF plus MC squared equals HF prime plus the total energy. And we found the total energy. We didn't need to, but we did. And then we subtracted MC squared from that to get the kinetic energy, to get 2.573 times 10 to the negative 16th joules.
Okay, the only notation I'm going to correct, the delta right there is you found the shift, right, as opposed to the wavelength itself. And so there's your shift, and then you added it to that number right there. And if you see what they mean about they didn't need to, instead of doing that, they should have just done kinetic energy plus MC squared, and then the MC squareds would have canceled. So basically what they did is they added on MC squared right here, and then once they got the total energy, they subtracted off MC squared to get the kinetic energy. And so just look at what the problem asks you to do, and that's my quick advice. Not wrong to do it this way, it just took one extra step, okay? Questions on that? That's the kind of more straightforward problem you can expect. I'm gonna share the other one. The group two had clearly this will stop the other one. Yeah, continue on. And okay, and so hopefully, yeah, you're seeing my my solution here. And I drew the picture, and you know, I had previously said that I saw 180 degrees as being like this, just kind of glancing. And as I'm rethinking it, that's probably considered 90 degrees, because when I wrote this problem, actually I copied this problem, head-on collision, photon comes in and bounces straight back, and that would be 180 degrees. Although, you know, somebody may argue that's 360 degrees. I don't know, that's 180 degrees, because the initial direction is here, the final direction is there, and the final direction being right there, and that's 180 degrees. So yeah, I'm going to go and call this 90. So I mislabeled it. I said the wrong thing when I was talking before. Okay, so the first thing you have to do, and I think I convinced this group that there's the initial energy. I don't want to do that. There's the initial energy of the photon, right? I want my annotate pen. Where is it? There it is. I don't want to make didn't want to make that box there, but hopefully you can see it. There's the final energy. There's the initial energy of the electron. It's just at rest. And there's the final total energy of the electron after it gets scattered. And so that is both kinetic energy plus MC squared, exactly the same issue that the group one had. Okay, but I am combining it together. You could have gone gamma minus 1 for kinetic energy times MC squared, and then added on MC squared, but those guys cancel then, right? And so there it is. Momentum. If you missed why this is the momentum of a photon, okay, probably want to take a look at that. But the bottom line is, for a massless particle, E is equal to momentum times speed of light. Okay, so momentum is equal to E divided by the speed of light, which is hc over lambda divided by c, and the c's cancel. That's what the momentum of a photon is. Okay, so I have the momentum of the photon before and after. And I'm going to have to draw this to a close quickly for you. So I'll just show you what I did. went too far. Do a momentum equation just like you would have done with Dr. Tech. Initial momentum, the electron has no momentum. The momentum of the photon after it scatters, negative sign because it's coming straight back, plus the energy. And then the bottom line here is you have to take these two equations and you got to combine them. The quickest way I saw to combine them was to take the first equation and multiply by C. I'm sorry, the momentum equation and multiply by C. And then I just did a linear combination. I added them, okay? And what you get when you add them is those two guys are two, and you know this because this is given in the problem statement. What is the energy of the incident photon? This is something
Okay.
you know, right? And then you're left with adding this side right here, which gives you that lousy thing. You got to push on the algebra a little bit on that. You got to manipulate gamma and all that to figure out exactly what the value is for you. And so you got to get rid of gamma right there. Okay, you got to get it into to U. You eventually solve for it, and you find that U is 0.651. Everything down here, though, is just algebra, right? Come on, I'm not getting the
So you
right.
multiplied by C to get from your H over lambda back to your
To
rest
get to
energy,
something
right?
that looked like energy. Yeah.
Gotcha.
Yeah, so it converted my momentum equation into something that looked an awful lot like an energy equation, even though it's
For
momentum.
systems of equations. That makes sense actually.
Yeah, it's just an algebra technique, right? When you got coefficients, you make the coefficients be the same. If one's negative, then they add to zero, and you've eliminated one of your unknowns. And one of your unknowns here, of course, is the wavelength afterwards. You got no idea what that is, so eliminate it. And then everything below that line right there is just the algebra to unmask where velocity is, as we said. Velocity is in two places. Directly in the momentum is U, but it's also hidden in gamma, as it was before. And so that's what all this rigmarole algebra is all about. All right, we're at least 5 minutes over. You probably got to go on to your next class, so I let you go. Again, Monday is an optional day. If you want to talk more about this, you got any questions about what I just did here, okay? Or if you want to go over any of the exam questions, we'll see you Monday at 11:30. If not, take the day off, all right? Have a great weekend. We'll see you all later on.
Thank you.
Thank you.
See ya.
I'll stop sharing this, and I'm going to stop.